over here I'll try to explain this from very basic. Okay, so what does this John-Tellar distortion actually means? So what happens over here that in a regular geometry of octahedral complex, this John-Tellar distortion is generally seen for octahedral complexes only. It is not seen that much for tetrahedral complexes. Okay, and I will tell you all the reasons that why is it so. Now, if you remember my introductory classes where I have explained that why d orbital split, there I have explained you that how your d orbitals are being assigned. Like you have 5 sets of d orbitals, like you have 5 d orbitals, among which you have 3 of those who are aligned in between of the axis, and two are those who are aligned on the axis. Like these are called your axial orbitals, like dz square and dx square y square, and these are like they are aligned along the axis. So whenever a ligand approaches towards it, or whenever a ligand comes towards it, they are more repelled or less repelled. Okay, so that the repulsion is directly based upon this thing, because these ligands, sorry, these orbitals are on the axis. Now since these ligands are not on the axis, they are in between of the axis, so they will not cause that much of repulsion. So these are the basic things which you have already seen. Okay, so I'm not going to repeat each and everything again. So what happens now actually that due to some, like due to asymmetrical filling of electrons, if electrons are not properly distributed among both the sets of electron, like among this Eg and T2g set of electron, set of orbital, if your electrons are not properly arranged or not properly distributed among these two sets of orbitals, the electrons are asymmetrically arranged. In that case, like it has been found that the regular octahedral geometry is lost. Okay, so we don't get a regular octahedral geometry. Instead of that, we get a little distorted geometry, which can be either Z out, that means tetragonally elongated structure, which means these two bonds are little elongated from the usual ones, or Z in distortion, or Z in structure, where it is also called as tetragonally compressed. Compressed means these two bonds will be little smaller than the other four. Okay, so that is the consequence, like that is the result of your John-Tellar distortion. That's very important to understand why is this happening. Okay, so see what happens actually that okay, let's say we are filling electrons in Eg and T2g orbitals. Now if I give more electron to Eg orbital, or okay, so if I have a Eg orbital, Eg orbitals are of two kind. Okay, the one is dz square and other is dx square y square. So dz square is responsible for electron density in the z axis, whereas dx square y square is responsible for electron density on x and y axis. Now if I give, okay, if I am filling electron and if I am giving the electron more electron to z square, means this particular orbital, because both of them are degenerate, means both of them are of similar energy, so I can give an electron to any one of them. So if I am giving more electron to dz square, in that case what will happen, that electron density along z axis will be more, and if a ligand will come towards, if a ligand will try to come from this z axis, so it will be repelled more. Okay, so in order to, so the repulsion will be more over here. So in order to minimize this thing, in order to if the complex will try to minimize this effect. Okay, and how that complex can minimize this effect, by enlarging the length of your z axis. Okay, by enlarging the length of the orbitals along the z axis. So that's why the z axis orbitals, they become little larger than the other four. Okay, than the x square and y square. Why it is so? Because electron density is more in z axis, so that's why they will be repelled more, and in that case it has to be little longer. If it becomes little longer, then it will be easier for that to adopt the electrons from the ligand, and there will not be much repulsion. Okay, so this is called your Z out distortion, and that is the property of complex. It acquires itself to a tetragonally elongated structure, so that it can form a stable complex. Okay, this geometry becomes little stable, little bit more stable. Now if instead of giving more electron to dz square, I give more electron to dx square y square, in that case what will happen, that there will be more energy, more electrons on the xy axis. So in that case your x and y electrons, or the orbitals along xy axis, they will be little elongated, and it will seems like your z axis has been shrinked. Okay, it seems like the z axis has been shrinked, but or it has been small, or it becomes a small. Okay, so that is called your compression or Z in distortion. Okay, so this is the basic phenomena which is happening over here. Now in which kind of in which kind of configuration we will see over here. So basically for high spin complexes, if I tell you, so for high spin complex you can see you have a D1. Okay, so for D1 I am just filling an electron in T2g orbital. So yeah, there are two kind of John-Tellar distortion. One is called static and other one is called dynamic John-Tellar distortion. When your electrons are filled, like when the electrons are asymmetrically filled in Eg orbital, that is called, that has more effect, and that is called a static John-Tellar distortion. Whereas when electrons are asymmetrically filled in T2g orbital, in that case, since T2g orbitals are not directly on the axis, they are in between of the axis, so they don't cause that much of repulsion, they don't cause that much of John-Tellar distortion. They are generally based upon the temperature, so that's why they are called as a dynamic John-Tellar. Okay, so just like in the first case, we like T2g is asymmetrically filled, so it will show a John-Tellar distortion, but a weak John-Tellar distortion. Same as over here also, because T2g is asymmetrically filled, so it will show a weak John-Tellar distortion. Now D3 will not show John-Tellar distortion, so that's why it is shown in red color. So it does not show John-Tellar distortion. Why? Because your Eg and T2g orbital are symmetrically filled. There is no electron. Symmetrically means equal number of electrons in all the Eg orbital and equal number of electrons in all the T2g orbitals. So there is 0 electron in Eg orbitals and 1 electrons in T2g orbital. So that's why this is symmetrical filling. Now this one will show a strong John-Tellar distortion. Why? Because you have electron in Eg orbital, and that too, like, that depends on in which you are filling. Okay, either in dz square or dx square y square. This is experimental value. This D5 high spin, it will not show John-Tellar distortion. Why? Because it is symmetrically filled, right? If you have equal, like you have two electrons equally filled in Eg orbital, and your T2g is also equally filled, 1 electrons in all the T2g orbitals. Your D6 will also show us a weak John-Tellar distortion, because your Eg is filled equally, but your T2g is not unequally filled. Now your D7 high spin will also give us a weak John-Tellar distortion. Why? Because again over here T2g is asymmetrically filled, but Eg is symmetrically filled. D8 high spin will not show John-Tellar distortion, because T2g and Eg both are equally filled. Okay, you have two electrons, 1 electron in Eg and 2 electron in T2g. D9 will show a John-Tellar distortion, and that too a very strong John-Tellar distortion, because your Eg orbital is not equally filled. There is 2 and 1 electron, so that's why it will show John-Tellar distortion. D10 will not show John-Tellar distortion, because it is like completely filled or symmetrically filled. Now talking about low spin complexes, so for low spin complex D1, D2 and D3, they are all same. Okay, so D1, D2, D3 will be like that only. D3 will not show John-Tellar distortion. Talking about D4 low spin, so it will show a weak John-Tellar distortion. D5 low spin will also show a weak John-Tellar distortion. Now D6 will not show John-Tellar distortion. Why? D6 low spin will not show John-Tellar distortion, because all your Eg orbitals are empty and all your T2g orbitals are filled with 2 electrons. So it will also not show a John-Tellar distortion. Talking about D7, so it will show a strong John-Tellar distortion. Okay, so D7 will show you a D7 high spin will show you, sorry, D7 low spin will show you strong John-Tellar distortion. D8 will not show you John-Tellar distortion, because T2g and Eg both are symmetrically filled. And then talking about D9, so in D9 orbital you have unsymmetrically filled Eg orbital, so it will show a strong John-Tellar distortion. So, and in D10 it will not show John-Tellar distortion. Okay, so it's very simple. You have to just see that whether Eg orbital is asymmetrically filled or not. If Eg orbital is asymmetrically filled, it will show a strong John-Tellar distortion. If T2g orbital is asymmetrically filled, it will show weak John-Tellar distortion. If like Eg and T2g both are symmetrically filled, or both are unfilled, or any one of, like all the Eg orbital are unfilled and T2g is completely filled, so in that case also, like they will not show a John-Tellar distortion. Okay, so this was the basic thing which I just wanted to tell you guys about how the John-Tellar distortion like happens. Okay, in the next video we'll try to understand it in more detail, like what kind of consequences you will get for John-Tellar distortion, and what kind of structure you will get, or what kind of splitting you will get for the d orbital in John-Tellar distortion. So that's all for this video, guys. I hope you guys like this. If you like this video, please rate this video, review about it, and follow me if you are not following me yet. I'll see you guys in the next video. Till then, have a great day. Bye bye. Hey guys, hello everyone, and welcome to an academy. So this is Nuruluda, and in this video we are going to talk about consequences of John-Tellar distortion, right? So in the last video we have understood that what is the basic thing, how that John-Tellar distortion actually occurs, and where does it occurs in a strong manner, or like where does it occur, like where the John-Tellar distortion is strong, where it is weak. So that's what we got to know over there, right? So now this is very important to understand the consequences of it, means what we are going to get into, like what we are going to like what is the effect of the John-Tellar distortion, like what are the things in the usual way which you can explain on the basis of John-Tellar distortion. So that is what I am going to do in this particular video, right? So okay, so the first consequence of John-Tellar distortion is the splitting of absorption band. So what it has been seen that generally for a d block element, for a transition metal complex, we get a broad peak like this. Okay, so we get generally a broad peak which looks something like this, and that is called your absorption band. Okay, so that is a broad absorption band which you generally get for d block element. Now what happens when a certain complex is taken where John-Tellar distortion is possible? Let's say we are talking about this. So we have titanium H2O6 plus 3. So over here titanium is in plus 3 oxidation state, so it's a d1 complex, right? So it's a d1 complex, and when it's a d1 complex, that means it has one electron in T2g orbital. That means the T2g orbital is asymmetrically filled. That means you have a weak John-Tellar distortion over here. Now due to that weak John-Tellar distortion, we know that this is T2g orbital and this is Eg orbital. In presence of this John-Tellar distortion, this T2g orbital splits into two parts, like the degeneracy is lost for these three orbitals. Similarly, the degeneracy of these two orbitals is also lost, and they also split up into two orbitals. Now the transition from this, the electron is over here, right? The electron is on the in the like the lowest energy orbital. So the transition of that electron can be from here to this level, or it can also be from here to this level. So the energy difference between these two, like between this one, is less, so it will be around 17,000 centimeter inverse, whereas the energy difference from here to this one is little larger, and that is around 20,300 centimeter inverse. So that's why what you are going to observe in the absorption band is a hump like thing. Okay, it's just like it won't be a clean broad signal or a clean broad absorption band. It will give you a little hump before that. Okay, so that means your absorption is being done at two different wavelengths. At different wavelengths your electron is being excited, and that is only possible when you have John-Tellar distortion over here. So what does it say is that according to Orgel diagram, okay, so Orgel diagram I haven't explained till yet, but I'll explain it very soon. So according to your Orgel diagram, one absorption is observed in D1, D4, D6 and D9. So all these four will just give you one absorption. Okay, they will just give you one absorption peak. So that should give you just one band. But experimentally it was observed that a peak absorption peak was also experimentally we observe peak at absorption band. Hence peak arises due to splitting of T2g and Eg orbital. So that's what you can say. So there is one more example given for titanium hexachloride. Over here also you have two bands which you will get. One is at one you will get at 13,000 centimeter inverse, and other you will get at 10,500 centimeter inverse. Okay, so this is how your absorption of splitting of your absorption band happens due to John-Tellar distortion. The next thing is the stability of copper plus 2 ion, and this is because, see, what happens actually that this there is a series given by Irving-Williams. So that is called Irving-Williams series, or you can call it as Irving-Williams series, whatever you pronounce it. So this series tells you that what is the stability of your positive ions. Okay, so you have a lot of dye positive ions which have been arranged experimentally based upon the experiment carried by Irving and William, and they have done a lot of work in this field. So they have arranged all these diatomic cations in the form of their increasing stability. But what you can see that from manganese, iron, cobalt, nickel, copper, zinc, you will see that the stability is increasing, but at zinc the stability is little less, and this copper plus 2 has a little higher stability than zinc, although the usual trend will suggest us that copper should have lower stability than zinc, but it not happens like that. So this is the reason behind is that this copper 2 plus complex are more stable than zinc plus 2 due to John-Tellar distortion happening in copper 2 plus complex, which increases its stability. Okay, so that's why this copper 2 plus become more stable. So this is second consequence. The third one is the instability of gold plus 2 ion. So your gold actually is not formed in plus 2 ion. Like you don't get a di-positive ion of a gold, you either get a tri-positive ion or you get a like mono-positive ion. So the reason behind it is that, okay, so this is how after John-Tellar distortion your orbital will split, and for gold plus 2 you will be having, like you have to fill 9 electrons, right? And since there will be more splitting due to it's a 5D element, so there will be more splitting, so the difference, this energy, this orbital will be so much far from here or from the nucleus, that this is so much far that taking out this electron from here is very easy for like it's very easy. So now if you fill nine electrons in it, so the last electron, the ninth electron, will fall over here, and because of staying, like because it's stay very far away from the nucleus, the electrostatic force of attraction for this particular electron with the nucleus is very weak, and that's why you require very less amount of ionization energy. So it becomes very easy for this electron to escape from here. Okay, so that's why your gold in plus 2 does not exist. It either goes out and it forms, like it gives you a gold plus 3. Okay, and if it is in gold plus 1, in that case it will not split, right? Because there you won't get John-Tellar distortion, so that will be filled up to here only, and you will just get a stable, like that time it won't remove because you don't get a splitting. So this thing you will not see in gold plus 3 as well as in gold plus 1. Okay, because John-Tellar distortion only happens in D9, like D9 complexes. John-Tellar distortion happens, it doesn't happens in D8, neither it happens in D10. Okay, so this is the third consequence. The last one is the instability of chelating complex. So it has been seen that your chelating complexes of your D9 system, they are not stable. Okay, so if I take a chelating complex of a copper, what I will see that copper actually shows you John-Tellar distortion, right? But copper 2 plus, and it shows John-Tellar distortion. But what is the effect of John-Tellar distortion? That these bonds will try to elongate, or they want to compress out, and due to that, if these bonds will try to elongate, in that case there will be a strain in these bonds. Okay, these are the bonds which are formed because of this chelating ligand. Okay, so if these bonds you want to stretch these two bonds, in that case you will feel a lot of strain in these bonds. Okay, so what will happen that due to this strain, due to this increase in strain or strain in the molecule, the complex becomes very less stable or very unstable. So this is what the consequence of your chelating complex, like the consequence of John-Tellar distortion on the chelating complexes we have. Okay, so that's all for this particular video. There were 4 consequences of John-Tellar distortion, and I tried to cover all of them. I hope you guys understood it well. I hope you guys like this video.